Welcome to the channel Physics Made Easy. Do you know what is the phenomenon behind the sparkling effect of diamond? Have you seen the cracks in the glass? They are shining like mirrors. What is the reason behind them? What is the reason behind the Mirage Formation in looming cold countries? Which phenomenon is responsible? You must have seen the optical fibers. Which phenomenon is responsible to carry message signal up to the long distances even the fibers are twisted? Then what is the phenomenon behind all these events and many more? We will discuss today in details, so stay connected till last of the video. We will discuss the process of total internal reflection, which is responsible for all the phenomena we discussed earlier. What is total internal reflection? First thing, as we are dealing refraction, but the word reflection is here. Normally we have seen reflection takes place from the shiny polished surfaces. Here in refraction, when light ray enters from denser to rarer medium, then what happens that at particular instant it is reflected. And why total? Because its 100% energy is reflected back in the denser medium. How it happens? Let's see. We have seen that if this is the denser medium, suppose I write with mu d, and this is the rarer medium, I write with mu r. This is the interface, that is the boundary separating both mu d and mu r. If light ray comes in this way, that is incident at this point from denser to rarer medium, then at this point if you draw normal, as we have seen in the case of refraction, what happens? The light ray bends away from the normal in going from denser to rarer medium. So it will move like this. This is the reflected ray, this is angle of incidence, this is angle of refraction. Okay, simple refraction. What is the law here? Snell's law, that is refractive index of this medium with respect to first is sin I upon sin r. But if you increase the angle of incidence in the denser medium, what will happen? The angle of refraction in rarer medium will also increase. You know, it's very simple. But at particular angle of incidence in denser medium, suppose I am drawing here, this is the normal, and at this point if you increase the angle of incidence in such a way that the reflected ray goes along the interface. Now what is the angle of refraction here? How much? 90 degree. Then angle of refraction in rarer medium is 90 degree. If light ray enters from denser to rarer medium, then the angle of incidence in denser medium is called critical angle. This is the definition of critical angle, that angle of incidence in denser medium for which the angle of refraction in rarer medium is 90 degree. That angle of incidence is called critical angle. Now, what will happen if you further increase the angle of incidence in denser medium? That is, angle of incidence is if more than critical angle. Here I can write this angle of incidence greater than critical angle. Now what will happen? Beyond 90 degree, that means the light ray will be reflected in the same medium following the rules of reflection. That is, angle of incidence will be same as angle of reflection. This reflected ray there is no polished surface. It can go from one medium to another medium. There is no hindrance. Despite of that, the refractive index of denser medium and rarer medium, the pair of media, is such that if the critical angle is lesser than the angle of incidence and the light ray is going from denser to rarer medium, reflection takes place. All this here and here refraction, but here reflection. And 10%, 100% energy is reflected back in the same medium. 100% energy is, almost 100% energy is reflected back in the denser medium. That's why this is called total internal reflection. So, what is total internal reflection? What is the condition for total internal reflection? Define critical angle. I discussed critical angle. What are the conditions for total internal reflection? One, that the light ray must go from denser towards rarer medium side. Its light rays must approach in such a way that they are moving from denser to rarer medium side. And secondly, the angle of incidence must be greater than critical angle for this reflection to take place. Now we will see what is the reason behind mirage formation. In desert places, the sandy ground is there, and during hot summer days, the sandy ground, their atmosphere becomes rarer as compared to the upper atmosphere. So what happens? Suppose there is a tree like this. From the top of the tree, the rays are coming towards ground. Suppose this is the ground. Then the rays are coming from denser to rarer medium. As compared to the temperature, higher will be the temperature at the ground. There is presence of sand, more heat is radiated. So this will be the rarer medium as compared to the upper layers. So rays are coming from denser to rarer medium. So they are moving away from the normal. What happens? At every point, the situation arises in such a way that TIR takes place, that is, the rays are completely reflected in the same medium here as I have shown. So what happens? If the observer is present here, then on extending back, it seems that the shadow of the tree is here. Then observer thinks that there will be some water present here, and in search of water, observer comes, but there is no water. So this is the reason behind the mirage. Also, in cold countries, the ship or boats at the lakes or the seas, this seems to be hanged in the atmosphere. This is called looming, the same phenomenon, total internal reflection. Also behind the shiny surfaces at the highways, at the roads in the hot summers. Now, we will see what is the function of optical fiber. Again, total internal reflection. In optical fibers, the strands, long strands of high fine quality of glass or quartz are taken of very small diameter, that is of the order of micrometers. They are made up of substances of different refractive indices. Inner wall of the optical fiber, long hollow pipe, is of larger refractive index, that is 1.7 as compared to the outer one. Suppose I am showing that if this is the optical fiber, then its shape I am showing like this, then this is the inner one and this is the outer one. Its outer refractive index material is lesser, that is about 1.5, as compared to inner one, it is refractive index 1.7. What happens when the message signal, that is light signal, you know what is the function of this optical fiber? To carry signal safely up to the large distances. Then which phenomenon is there? Total internal reflection. I have written light signal. When light signal is, suppose, enters in this optical fiber, then due to TIR, multiple TIR, multiple total internal reflection, how the ray is going from denser to rarer medium, then it is reflected again. 100% energy is safe and it is transmitted up to the long distances. What happens in the endoscopy? The light pipe is used to watch the internal organs by the doctors. Light signal is entering here, and as it enters, it goes from denser to rarer medium. First condition of TIR is obeyed, and second, at every instance of its incidence at this surface, its angle of incidence always remains greater than critical angle. So it is reflected in the same medium. Electrical signals are also transferred by this optical fiber. How? Electrical signals are first converted in the light signal by using a device called transducer. You know, transducer is a device which converts one form of energy into other. So electrical energy to light energy, and at the receiving end, again the light energy is converted into electrical energy. So again you get electrical energy transferred from one place to other place. Similarly is the diamond, its sparkling effect. You know, ordinary we have seen that in case of diamond, its cutting is very, very important. What happens? For diamond, the critical angle is very, very less, around 24 degree, and its refractive index is also about 2.4 or 2.5. High refractive index and less critical angle. The light enters, once the light enters in diamond, it remains trapped and it comes out for very few directions. In the few directions, the sparkling effect, all the light rays come out from in that direction. So it is the reason behind the sparkling effect. So at all faces, total internal reflection, mostly at all the faces, total internal reflection takes place, and in certain very peculiar directions, when angle of incidence is less than critical angle, then light comes out and it produces the sparkling effect. Now we will see what is the relation between critical angle and refractive index. As we have seen, for TIR to take place, the ray should go from denser to rarer medium, and critical angle is that angle of incidence in denser medium for which the angle of refraction in rarer medium is 90 degrees. So this is, suppose, incident ray, this angle is critical angle, this angle of refraction R equal to 90 degree, and this is the ray going along the interface. You know what is the Snell's law? Refractive index of second medium with respect to first medium equal to sin I upon sin R. Using that, if you write here, what is I? In place of I, we have written critical angle. So sin C upon sin 90 will be mu R upon mu D. That is refractive index of this rarer medium with respect to denser medium. What can be written? This refractive index, that is refractive index of denser medium with respect to rarer medium. You will have to reverse it. And sin 90, what is sin 90? 1. So you will write this 1 upon sin C. So in fact, the refractive index of the medium is inversely proportional to sin C. What are the other factors affecting this critical angle? Material, its refractive index, as it is clear. Temperature, as we have seen in Mirage Formation, the sandy ground, there is larger heat is reflected back. So heat radiated back is more, temperature is more, so medium is rarer. Also the color of light. You know, big Bohr, from violet to red, the color's wavelength is increasing. So on that factor. What happens here in case of certain substances for glass air interface, and if you take the prism, what I am going to tell you, it's very important that if a prism having one angle 90 degree and other two angles of 45 degree, right angled isosceles prism, then bending of light rays can be made by 90 degree, by 180 degree, and also the prism can be used as the erecting prism. How? Let's see. Look, in case of prism, if you have two sides same and one angle, this is 90 degree, then these two angles are 45 and this is 90 degree. What happens that the ray of light which comes here from air to glass, but it is perpendicular to this surface. Suppose I am writing the name A, B, C. What will happen? Will it bend if it is going perpendicular to the surface AB? No. So it will move straight and come at this point at the surface AC. What will be here? The angle of incidence. Is it? No. How will you find the angle of incidence? By drawing a normal perpendicular at this surface. Now this is 90, this is also 90, this is 45, then this will be 45 and this will be also 45. So this is 45 degree. It has been observed for glass air interface. If this is glass, then critical angle for glass air interface is about 42 degree. What is here? Angle of incidence is 45 degree. So angle of incidence is greater than the critical angle. Which phenomenon will take place? TIR. So following the rules of reflection, it will reflect from this point. Although there is no polish, it can move on this side. But due to TIR, as its angle of incidence is greater than critical angle, its total internal reflection takes place. Now for the surface of this BC, it again becomes normal, so it comes back in air again. So we see that bending of light rays is by 90 degree. Another case, if you place the same prism but in this way, here if you see that 90 degree prism is there, this is the angle 90 degree, these two are 45 degrees again. But how the light ray enters? Look, again the light ray enters normally, so it will not bend at this point. This is suppose A, B and C. At this point again you will find that this will be the angle of incidence, which will be 45 degree. This is 90, this is 45, this is 45, so this is 45, which is more than the critical angle for air glass interface. So it will not go beyond AB. It will be reflected obeying the rules of reflection and come at the surface BC. What will happen? Since at angle B 90 degrees angle and this is 45, because this is 45, so here if you draw the normal, again you will find the light ray strikes the surface BC again at 45 degree more than critical angle. So what will happen? It will reflect obeying the rules of reflection. So you know, incident ray is this one, reflected ray is this one. How much is the bending? 180 degree. So to bend the light rays by 90 degree, you have to keep the prism like this, and to bend the reflected rays by 180 degree, you have to keep the prism like this. Third, erecting prism. In this case, if we see, the prism is placed having its shorter face, that is 90 degree angle is in the vertex here in the top position, and these two angles are of 45 degree each. If the light rays enter at the shorter phase like this. Okay, then simple refraction takes place here. This is the first ray, suppose this is the second ray, then simple refraction takes place here. And what happens at this surface, if you, I am drawing again, this is the prism, suppose this is, then what happens at this hypotenuse, TIR, total internal reflection takes place. Then this is the reflected ray here, this is the reflected ray here. Then what happens that the rays reflected from the hypotenuse are again coming back from the surface AC, and they are going in this way, this one. This is the two arrowed ray, this is the single arrowed ray. We can see here that if the object is placed here, then its image is erected like this. So this is an erecting prism. See the question based on total internal reflection. First question says a small bulb is placed at the bottom of a tank filled with water to a depth of 80 centimeter. What is the area of the surface through which light from the bulb emerge out? Refractive index of water is 4/3. I have drawn here this figure. Suppose at point B the bulb is placed through which the light rays are reaching at the surface of water. Which area of the free surface of water will be illuminated till the light rays are entering from denser to rarer medium, having their angle of incidence less than critical angle? They will deviate away from the normal in the rarer medium. But what will happen at the critical angle? Suppose at this point P, the light ray goes and its angle of incidence in the water, that is in the denser medium, is C, equal to critical angle. Then it will go along the interface on this side also and here also. So a circle of illumination, or you can say this cone of illumination, will be observed here, and this critical angle will be same here for this height AB. It is given 80 centimeter. I have written height 0.8 meter. What is the relation for refractive index of water? Mu, that is 4/3, equal to, mu equal to 1 by sine C. So you can write here this sine C will become 3/4. If you draw a right angle triangle, then this is 3, this is 4, and this is C, perpendicular upon hypotenuse. Then what will be the base here? This will be 16 minus 9, that is √7. And if you find the tan C, this value, in the triangle APB, this one, what is tan C? If you see, the radius of the circle is R and this is 0.8. So from the triangle you can write here R upon 0.8, and from this relation you can find the same tan C, which will be perpendicular upon base, that will be equal to 3 upon √7. Look, I have written from the figure and from the sine C triangle relation of critical angle and refractive index values. You can find simply R, that is 0.8 into 3, 2.4 upon √7. What will be the area of the circle? You can find what will be the area, this one, pi r square. So it will be pi, that is 22/7 into r square, so 2.4 into 2.4 upon 7. This root will be removed. So you can calculate, it comes out 2.59 meter square. So in this way the area can be calculated. It is given. How will you calculate the fraction of energy emerging out? The fraction of energy emerging out can be given as, if IS is the intensity of source, then the energy released through solid angle, this is the solid angle. So energy released through solid angle will be intensity into omega upon energy released through 4 pi. So if you write here, this is Is upon 4 pi. What is the relation for solid angle and this angle? You can write here, I have shown this angle C. Then learn this relation is omega is 1 minus, this is a relation between solid angle and this angle C in the figure. 2 pi 1 minus cos, I will write here this angle C. Use this and you can find how to calculate energy, fraction of energy emerging out. Now come listen, question 2. In this right angle isosceles prism, which color will be refracted from the surface AC if the red, green and blue lights are incident at the surface AB normal to it? The refractive index value for red color is 1.39, for green color 1.44 and for blue color 1.47. How will you solve this question? You know the relation for refractive index as mu equal to 1 upon sin C. This implies that C will be sin inverse 1 upon mu, because sin C will be 1 upon mu, then C will be sin inverse 1 upon mu. Calculate these values. If you write here mu for red color, then for red color C will be sin inverse 1 upon 1.39 and it comes out 46 degree by observing the values in sine table. Using sine tables, it has been observed that critical angle for green color is 44 degree and critical angle for blue color is 43 degree. Now what happens? All the rays are normal at the surface AB, so they will enter in the same straight way, that is like this, and they all will strike the surface AC at what angle of incidence? Can you guess? This is 45, this is 90, so all are striking the surface AC at the angle of 45 degree. Now for angle of incidence 45 degree, the critical angle for green and blue color is less than 45. So angle of incidence for these two colors is more than critical angle, so they will be reflected back, that is TIR will take place with the green and blue color. For red color what will happen? The angle of incidence is 45 but critical angle, the critical angle is 46, so it will come out. So refraction will be for red color. Next question, it is asked in AIPMT 2014. The angle of prism is A and one of its refracting surfaces is silvered. Light rays incident at angle 2A on the first surface returns back through the same path after suffering reflection at the silvered surface. Find the refractive index of the prism. How will you draw the figure? Look, you have to show the prism having the one surface silvered, and angle of incidence for the light ray at the surface which is unsilvered is 2A and angle of prism is A, as I have shown here. What will happen? Suppose this surface is silvered. Okay, I am showing a little bigger this one. Suppose this is the diagram of prism. So what happens? From the silvered surface, it is given that the light ray comes, retraces its path, comes back. You will draw the normal and it is given that angle of incidence is 2A. So normal and incident ray, this angle of incidence is 2a. The light ray in going from rarer to denser medium will bend towards normal and it is retracing its path. What does it mean? That it will bend in such a way that it will make 90-degree, because only then it is said that the light ray is retracing its path like this. It is going and it is coming back from the silvered surface, this one. This angle will be 90. What will be this angle? Look, if I am writing the name here, M, P, Q, suppose this point as T, then this point as S, then angle MTS. What will be this angle? 90 minus A. This is 90, this is A, so this will be 90 minus A. This total is R, this 90-degree, then what will be the angle R here? Angle R means refraction, angle of refraction, normal and refracted ray. So what will be the angle R here? Look here, 90 minus this one. You will write here 90 minus angle MTS, that is 90 minus A. Okay. So the refracting angle of refraction is also A. Apply the Snell's law. What is Snell's law? Refractive index is sin I upon sin R. Put here, what is the refractive index value, angle of incidence? You will find here, you will write sin 2A upon sin A, as R is A and angle of incidence is 2A. In place of this you have written, what is sin 2A? 2 sin A cos A upon sin A. So what is the refractive index? Only 2 cos A. This is the answer. In this way you have to solve. So today we have seen the phenomena based on TIR, total internal reflection, and how to solve numericals based on that. Hope you must have enjoyed it. Thank you.